Cantor's theory of infinite sets revolutionized the understanding of the concept of infinity and paved the way for profound developments in mathematics. Developed by the eminent mathematician Georg Cantor in the late 19th century, this theory explores the intricate properties and cardinalities of infinite sets. By introducing the notion of bijections, Cantor challenged conventional mathematical wisdom and opened up new vistas of exploration in set theory, topology, and other branches of mathematics. In this exposition, we delve into the basics of Cantor's theory of infinite sets, uncovering its profound insights and mathematical intricacies. Cantor's diagonal argument and the power of infinity. Central to Cantor's theory is his celebrated diagonal argument, which demonstrates the uncountability of certain infinite sets. Cantor's groundbreaking insight was that not all infinite sets have the same size, leading to the classification of infinite sets by their cardinalities. He showed that the cardinality of the set of real numbers, R, is strictly larger than the cardinality of the natural numbers, N, thus establishing an infinite hierarchy of infinities. The LF numbers and cardinality. To quantify the sizes of infinite sets, Cantor introduced a new notation using the Hebrew letter aleph. The smallest infinity, denoted as 0, aleph null, corresponds to the cardinality of the set of natural numbers. Cantor then defined larger aleph numbers, 1, 2, and so forth, to represent progressively larger infinities. Remarkably, Cantor proved that there is no largest aleph number, thus revealing the vastness and richness of the infinite realm. Cantor's theorem and the continuum hypothesis. Cantor's theorem states that the cardinality of a set is strictly smaller than the cardinality of its power set, which consists of all its possible subsets. This result, along with his diagonal argument, established Cantor as a pioneer in the study of transfinite numbers. Moreover, Cantor formulated the continuum hypothesis, which conjectures that there is no cardinality between that of the natural numbers and the real numbers. This hypothesis, though undecidable within the standard axioms of set theory, became a driving force for further investigations into the foundations of mathematics. Set theory and beyond Cantor's theory of infinite sets had profound implications for the field of set theory. It established a rigorous framework for analyzing infinite collections of objects and inspired the development of axiomatic set theory. Cantor's ideas also played a crucial role in the investigations of the mathematical foundations and led to the development of Zermelo-Fraenkel's set theory with the axiom of choice, ZFC, which forms the basis of modern set theory. Cantor's legacy and impact. Cantor's theory of infinite sets revolutionized our understanding of infinity and set theory, shaping the landscape of modern mathematics. It provided the tools to explore infinite structures and paved the way for groundbreaking advancements in diverse fields, including mathematical logic, topology, and analysis. Cantor's ideas continue to inspire and challenge mathematicians to this day, stimulating ongoing research into the mysteries of infinity. Cantor's theory of infinite sets stands as a testament to the power of mathematical insight and ingenuity. By unveiling the profound and intricate properties of infinite collections, Cantor forever transformed our understanding of the infinite and its role in mathematics. His work not only expanded the frontiers of knowledge, but also ignited a fervent pursuit of mathematical truth and sparked a paradigm shift in our perception of the infinite.